Okay, so now that we've seen an example of a first-order differential equation being solved using Laplace methods by setting up as a linear system of equations, a linear equation, what I'm going to do now is do a second-order differential equation of the non-homogeneous type, just to show you just how easy it is to solve these equations using Laplace. So let's go in. We're going to be having a look at d2x by dt squared minus 3 dx by dt plus 2x equals 2e to the 3t. Okay. So let's have a look at this. So first things first, let's get our definition. So the Laplace transfer of x, we're going to call that x bar. Yeah. And really, remember, this is really saying that the Laplace transform of x is going to be a semi-infinite integral of x e to the minus st dt, which also we can abbreviate to f of s. Okay, we're just using that as our abbreviation here. Okay, and now let's have a look at the first derivative, which is dx by dt. We're using the x dot to abbreviate that. It's going to be s x bar minus x naught, and the Laplace transform of x double dot, so that's d2x by dt squared, which is what we have over here. That's going to be s squared x bar minus x naught minus s to the power of naught x1. So now what we can do is say, well, the Laplace transform of the left-hand side is going to equal the Laplace transform of the right-hand side. Yeah? And from the principle of linearity, then, we can say that the Laplace transform of the whole left-hand side is going to be the Laplace transform of d2x by dt squared minus the Laplace transform of 3 dx by dt plus 2 times the Laplace transform of x equals the Laplace transform of 2e to the 3t. So I'm going to go straight into that and say the Laplace transform of d2x by dt squared is going to be s squared x bar minus sx naught minus x1. So let's write that down straight away. S squared x bar minus s x naught minus x1 minus 3 dx by dt, which is going to be s x bar minus x naught plus 2 times the Laplace transform of x, which is x bar, equals 2 times the Laplace transform of e to the 3t, which is 1 over s minus 3. Yeah? So now let's simplify this a little bit. So we can say that this is going to be, see that there? It's going to be s squared x bar minus sx naught minus x1 minus 3sx bar plus 3x naught plus 2x bar equals 2 on s minus 3. Now, the one thing I forgot to do was mention what the initial conditions are. So, and the question actually says over here, when t equals 0, x equals 5, and dx by dt equals 7. Yeah? So we can say that x naught equals 5 and x1 equals 7. So let's substitute that back into here. So we can say s squared x bar minus 5s minus 7 minus 3s x bar plus 3 times 5 is 15 plus 2x bar equals 2 on s minus 3. Okay, so now let's simplify that a little bit more. Let's go up. So we can say s squared x bar minus 5s minus 7 plus 15. Okay, 8 minus 3sx bar plus 2x bar equals 2 on s minus 3. 3s x bar, 2x bar. So now let's collect the x bar terms. So we have s squared minus 3s plus 2 minus 5s plus 8. And I think that's right. Equals 2 on s minus 3. Yep. So now let's take the minus 5s plus 8 to the other side. So we can say x bar, s squared minus 3s plus 2, equals 2 on s minus 3 plus 5s minus 8. S minus 3 on s minus 3. So we can say now that x bar, s squared minus 3s plus 2 equals 2 plus, okay, so we'll have 5s squared plus 24 minus 8s minus 15s, all on s minus 3. So we can now say that x bar okay, and we can see that this is actually going to factorize here to s squared plus 2, yeah, that's going to work, equals everything that we had on that side. So we can say now that x bar is going to equal 5s squared minus 23s plus 26, all on s minus 3, and then we're just going to divide by s minus 2 and s minus 1, s minus 1, and s minus 2. So that's what x bar is now. Now what we can do is if we find the inverse Laplace transform of the left and right side, we're going to find what x equals. So that's what we're going to do next. So that's what we had before. We know what x bar is. And we know that in partial fractions, that's going to be a on s minus 3 plus b on s minus 1 plus c on s minus 2. And to find those partial fractions, I'm going to use limits. So I'm going to say for a, we're going to take the limit as s tends to 3 for 5s squared minus 23s plus 26, all on s minus 1, s minus 2. So that's going to be 5 9s 45 minus 23 times 3 minus 69 plus 26, all on 3 minus 1, 2 times 1. 45 minus 69 plus 26 is 2, on 2 equals 1. So that implies that a equals 1. This is actually quite a nice way of, of using, it's called the cover-up method, to find what the values of a, b, and c are in partial fractions without having to do anything too messy. So it only works with linear factors as well, but it's a nice trick. So I'll do it again for b. So for instance, if we want to find b, we take the limit as the denominator tends to 0. So that's going to be when s equals 1. So we'll do that. The limit when s tends to 1. And you write the denominator, or the numerator always on the top, which is always the same. 5s squared minus 23s plus 26, all on the remaining denominators, so not the one that you're working with. So it's s minus 3 and s minus 2. So it's going to be 5 minus 23 plus 26, all on 1 minus 3 is going to be minus 2, times 1 minus 2 is going to be minus 1. So that's going to be equal to 5 minus 23 plus 26. That's going to be 8 on 2 is 4. So we can now say that that implies that B equals 4. And A equals 1. And for C, we'll take the limit as S tends to 2. For 5s squared minus 23s plus 26 on s minus 3s minus 1. So 4 times 20 minus 46 plus 26, all on minus 1 times 1. So that gives 20 minus 46 plus 26 equals 0 on minus 1 equals 0. Okay, so we can now say that x bar equals 1 on s minus 3 plus 4 on s minus 1. Yeah? So if we take the inverse Laplace transform, the left-hand side, we're looking to find the inverse transform of the right-hand side. So we now can say that x equals e to the 3t plus 4e to the t. And there we have it, the final solution to the differential equation of d2x by dt squared minus 3dx by dt plus 2x equals 2e to the 3t, where x equals e to the 3t plus 4e to the t.